Hey, in the back, you have these sheets. It's also online for the trig functions. All the rules, the laws of cosines, laws of sines, laws of tangent, the unit circle, half angles, the product of sums, odd, even functions, everything you need to know, remember about trigonometry to help us, because that'll be the hardest part on this course. As well as in the last page, you'll have rules of derivatives and integrals. We will be referring to these a lot. And then same thing in the back, we have, yeah,
Because that's calculus.
but yeah, this, as you see here, so here are the derivatives and here are the integrals. So the integrals, you won't, once you see it here, you can always just use it. Because once they've been defined, you can use them. Common derivatives, the most common ones.
So for the notation, you can use the prime notation or the
dy dx. Actually, I'm glad you said that, because in calculus 1, you should have learned y prime or f prime dy dx dx partial. There are a whole bunch of different symbols you can use for derivatives. So whatever's easiest for you. It looks more impressive if you do it this way. This is just a lot of writing. But like we do same thing, yeah, because remember in algebra, when we first start talking about functions, you learn this. So that then it just goes with that.
It just means the derivative.
Derivative, right? Okay. Which is what we're going to talk about today. We're going to define. We're not going to actually, not today, but we're going to start leading into it, because remember, the whole thing about derivatives this is what we've been talking about. Last time I referred to it, derivative equals a slope. All right, so Galileo started talking many years ago. He was on the Leaning Tower of Pisa. He would go up to the very top and drop something. Well, he actually dropped it inside. He first dropped it outside, then he dropped it inside to see if there was a difference. Why would he do that? Yeah. Air resistance. Because that's why whenever you talk about falling objects, usually in physics, engineering, you'll say in a vacuum. Vacuums are the perfect environment because there's nothing else acting upon it except gravity. And after more and more tries, he came up with a formula, or the rate of gravity. Do you remember what that was? What is it in SAE? So that's where we found out that is it 15 feet per second squared. Per second. So all depends if you're dealing with metric or SAE, which is everybody else. Metrics, yeah. In physics engineering, you always use metrics. There have been instances, I mean, not in the near distant past, is that one group was using American system, one group was using metrics, and it doesn't fit.
You have to convert.
You always are, and that's why I said universally for engineering and physics, you always use MKS, meters, kilograms, seconds. Stay with the metrics. So what he figured out is after dropping all these things, he came up with an average speed of falling objects. How would you figure out the what does the average mean? How would you find the average of something?
Taking all these samples, adding them together and dividing.
Right now, how would you do it with respect to speed? Because now you're right. This is the average of over all of them divided by chat. Now we have another word, speed. How do you calculate speed?
This hour.
Right. So now we're looking at the average distance over time or elapsed. Because what you're looking at here is when you first hold it, T sub 0 is 0. And then along the way, you can figure out at different times, you can figure out now that we have the constant gravitational acceleration, it's the acceleration, that's why it's squared. It's the second derivative of speed. So now that we know the time intervals and we know the constant rate of an object falling, we can figure out the speed at any given point. Assuming, of course, that there is no external force acting upon it. Wind, fog, snow, cold is another thing, because do objects fall at the same rate everywhere? No. They fall different from sea level to top mountaintop. The main reason is because the air density. It's less dense at altitude. That's why you have to, whenever you climb mountains, you have to bring your own oxygen. At the ocean, you have nothing but oxygen. So the formula for average rate, average speed of an object. When we'll use it as a function notation. So we have the average speed equals TNH. Well, let's say T1H. What does that represent? No. Actually, I shouldn't use that. I should use parentheses.
So T1 is going to be the time at
Which axis is going to be represented on? X. Time, always x-axis. Time is always x-axis because it never stops, it never goes back. And in any formula, like even slope, it's rise over run. This one always goes to the right. It can go up if it's positive, down if it's negative, but the bottom's always so x value always goes. So this is average speed over this. Over this equals the distance traveled over the elapsed time, which is equal to. Now, since we have 2 points, we have the beginning, the first point, and it goes on to another one, T2H. H. H1, H2, because they're different heights if it's dropping. So it would be H2, height 2 minus height 1 over time 2 minus time 1. But remember, it's a function of time. So the height, the position is a function of time. F of T2 minus F of T1 over T2 minus T1. For example here. And eventually we're going to define T2 minus T1 actually defines what variable? H. Here's our first example. So this is where you start, and this is where you end. That's the distance traveled. Here's an example. A rock breaks loose from a tall cliff. Here's the rock. It breaks loose. What is its average speed? A, during the first 2 seconds of fall, and B, during the 1 second interval between 1 and 2. So how do we go about doing this? What's the difference? Actually, if you look at what's the difference between these two? On the first one? On second one? Right. Very good. That's the big difference. For A, it's between 0 and 2 seconds. And from B, it's between 1 and 2 seconds. So there's our times are going to be these now. So the average speed the formula is F of T2 minus F of T1 over T2 minus T1. Now the question, what is our function? Actually, it's a function of time, I should say, T. What function are you dealing with? No, that's what we're looking for, but we have to have some function defined here. This is the rate of the falling object.
That's correct.
Very good. Yeah, because it's function of time. So it's either going to be 16 t squared or 9.8 t squared.
Well,
we don't want to deal with decimals just yet. Let's use this one. I don't want to deal with decimals just yet. So in A, T1 is 0, T2 is 2. So since f of t equals 16t squared, we have 16 2 squared minus 16 0 squared over 2 minus 0. Is that right? No. What's wrong about it?
That's,
What's important in physics? And all your answers have to have what? Units. What units do we have? It's an average speed. So we know it's going to be feet over time, or feet over seconds, you're right. Is it squared or is it just regular? Let's look at it. Up top here, we have 16 t squared is the unit. Down here, it's t. So we only have 1 second. So it's 32 feet per second. That's the average speed of the falling object. Because remember, what is the unit of speed? It's not squared. The velocity, acceleration is squared. Velocity and acceleration increase it. How about for B? We have T1 equals 1, T2 equals 2. So it's f of 2 minus f of 1 over 2 minus 1. We're using this function, 16t squared, so it's 16 2 squared minus 16 1 squared over 2 minus 1 is 1. Sixteen times 4 minus 16 times 1. 64 minus 16 equals, what I put? 48 feet per second. That's the average speed. Do you always want average speed? Yes, and what's that called? That is called instantaneous speed. How do we find instantaneous speed? Because this is speed at one point in time. So if you think about what happens, let's look at this. Let's draw a graph. This is T1 and this is T2. And this is our function, our speed. Because when we find average speed, this is what we're looking at. This is average speed. This huge distance here. Now, as this gets smaller, as these get closer together, then we get instantaneous speed. So we have to look for smaller and smaller and smaller and smaller and smaller intervals. So how do we go about doing that? Let's look at example 2. This is example 2, which I'll finish writing down. How far is the distance around here between T1 and T2? How far is that distance? That's what H is. Because T1, that's where you start off with, right? How do we get to T2? That's the interval we're looking at. So this is T1, this is T2. So because remember, we want to only use instantaneous distance. So we have to read everything in our average function everything in here has to be written as only one time. Only one time. T1. So, oops, yeah. So notice what, that's T2 minus T1, I'm sorry. So what we have to do is we have to write T2 in terms of T1. We have to write T2 in terms of T1. So far, so good? So, in other words, looking up here, because we know that, back to this, T1 plus H equals T2. If we subtract T1 from both sides, what do we get? Which is what this is. So that bottom now becomes H. And here, to get from T1 to T2, we have to add H units. So T2 is actually T1 plus H. This is the instantaneous speed. Can you tell me why it's called instantaneous speed? Only has one time. T1. Everything in this equation only happens at T1. And that's the instant we want. So now let's look at example 2. Ready for example 2? Here's example 2. A rock breaks loose from the top of a tall cliff. Find the speed at T1 and at T2. Two separate questions. This is A and this is B. So how do we go about doing this?
So we need to find the speed at the instant of where the object is at once. So then we
Right.
have to set up the formula, which would be f of t1 plus h, and we know h equals 1 because 2 minus 1 equals 1.
We'll do it again. We'll treat both these separately. One equation has to work with this.
Okay.
And then these are two separate. This is part A, this is part B.
Okay.
They can give us two separate answers.
So T1 is going to be, so H equals 1 to 0 plus
Are we finding the average speed or instantaneous speed?
instantaneous.
Which starts off as the average speed. The same formula, but we use H in the bottom instead. So let's first put our formula we're dealing with. F of T1 plus H minus F of T1 all over H. This is actually the change of Y over the change of X, which is what a slope really is. And in algebra, we call this formula the difference quotient. So that's the formula let's use. Now, in our case, we have 16t squared since we're going to use the SAE system, the non-metric. So this equation, delta y over delta x, will become 16t plus h squared minus 16t squared all over h. This is the formula we'll be using for our example, for a free-falling object. No external force acting on it. So for A, T is 1. Remember, we started off with the average speed of the object, right? We start with the average speed. We need to see what value does the equation approach as h gets smaller. Here's what it's saying. Because remember, the whole thing about instantaneous is we have to approach a specific value. So when that, let's look at the first one, when h is equal to 1. So we have 16, t is 1, h is 1. One plus one is 2. So we have 16 times 4 minus 16 times 1. 64 minus 16 is 48. Okay, that's when T1 and T2 are 1 second apart. What if h is equal to 0.1? So we have 16, t is 1, h is 0.1 squared plus 16 times 1 squared over 0.1. Yeah, go ahead and work this one all the way out. Now remember, it started off at 48, now it's at 33.6. So we go a little bit smaller, 0.01. One plus 0.01 squared minus 16 times 1 squared, 0.01. 1.01 squared minus 16 over 0.01.
32.6.
15. Actually, because we have to do this a couple more times. And we go 3, every time it gets more and more. Then we have to do it for t equals 2. So it's a lot easier if we use Excel. So when t sub 0 equals 1, this is my h. It's average sped.
No, it's
That's even worse. There. So this is when h equals 1, h equals 0.1, h equals 0.001.
so we're trying to get h as close to 0 as possible.
Right, because remember, we're trying to go from T1 to T2, move T2 a lot closer and closer. So the h gets smaller and smaller and smaller and smaller and smaller. Eventually, it gets to be the same one. So you see what number it's approaching.
32.
It's approaching 32. So if T1 or T sub 0 equals 1, then it approaches 32. But if we look at it from 2 seconds, it starts off at 80, and now it's approaching 64.
Our what starts off at eight?
This is when t equals 2, h equals 1, our value. This will start off at 48, our first value. When it's 1 second apart, it started off at 80.
Okay.
Now we're at 64.0016. So you see, the further we keep on going, the smaller this gets, the closer it gets to the 64. So this one would is 64. And this one would equal 32. And that's how we find the instantaneous. It's not, here's the sucky thing about it. If it's looking for instantaneous, you can't just jump straight in there and do a calculation. You have to do a series of them and see what is approaching. Yes, calculators would work great for it, but a spreadsheet, because all you have to do is once you put it in there. The hardest part is putting in the formula. Was
Yeah, I imagine, because then you have to actually do that.
Yeah, you have to break it down because it has to be, the formula has to be as we wrote it. We read it. It has to be this. So you have on Excel, what you have to do is equal sign. Now the top number, 16 times parenthesis, let's say A1, but this has to be a fixed number. So I have to put that in dollar signs because it can't move, plus B1 squared minus 16 times B1, times B1 squared, or T1, this has to be the A1, because it's constant, divided by what your B value is. Yeah, the hardest thing about this one is this equation and this equation have to be inside that major parenthesis. So that's the beauty. That's why I like Excel. It's a very, very low level programming language because you have to program the formulas in there.
So this, you can get limits.
That's how you'd find it, yeah. Actually, no, there's much easier ways to find limits. Because that'll be your hell week, is learning how to do limits using the formulas, the definitions, proofs. But then once we get to the shortcuts, the formulas, you can do them in a snap.
Okay.
For example, I know that if I keep on going, it's going to go down to 32. But at this pace, it's getting close to 33. We're going to see that the derivative of this thing is 32t. But again, that's for another day. Once we start learning how to do derivatives,
And so the limit, the derivative of the limit.
it's going to go the same thing, right? Because you're jumping ahead. But yes, you're ruining my future lectures. But yes, that's exactly what we're going to start defining later on in this chapter. Is we're doing just algebra, the average speed, the instantaneous speed. But you notice here in instantaneous, it started off saying instantaneous speed happens this is T1, this is T2. Instantaneous speed happens when this value gets closer and closer and closer. In other words, what happens is the distance between here goes to 0. That's what limits are all about. We'll get to that in a little bit, but that's what it's all about. That's going to be your limit. That's going to be your derivative. That'll be what we're looking for here is once we find this value here, because if you think about it, T2 minus f of T1, T2 what is that formula right there? Yeah, it said that it's delta y over delta x. It's a distance formula, yes. But let's look at this thing. On the horizontal axis, what is this axis, x or y? So T2 is x2 minus x1. This is the same as the y values. This is what we did in algebra. So now we're going from algebra, we're introducing ourselves to calculus. But you'll see that we'll be trying to use a bunch of more sophisticated formulas. Calculus, if this is your entire equation, the whole process from the start to stop, calculus is right there. The rest, algebra and trig.
So it's all, calculus is only a small.
It just starts the process. That's it. But you have to know what process to do first. That one small part will save you, because then once you get this thing started, the algebraic process is just mechanical. So that's the hard part, is knowing where do we get started. So calculus gets the ball rolling, and then it goes from there. All the mechanics is algebra. So let's look at, we never solved that, did we? No. So let's look at this equation. Remember, this is what we said we're going to do. We haven't done it yet. So we have delta y over delta x. In our example is 16t plus h squared minus 16t squared all over 8. Remember, h is t2 minus t1. As T2 and T1 get closer together, H gets smaller and smaller and smaller. Eventually it goes to 0. So what do you have to do first? Yeah. How do we do that? Yeah. That's exactly what it means. So this is simply T plus H times T plus H. Let's look at the long way also. So T times T is T squared. T times H is TH. H times T is TH. H times H is H squared. Combine the middle terms, which is what that is. Well, I did take T times T is T squared. T times H is TH. H times T is TH. H times H is H squared. These are both the same, so I have to combine them. And that's what goes inside here.
And we have 16t squared plus 32t plus 16 squared.
Right. So next thing we do is get rid of the parentheses. Distribute. 16t squared. 16 times 2 is 32th plus 16 times h squared. Whenever you do this, the difference quotient, whatever's after the minus, this number here has to be canceled by something. Whatever's after the minus, if it doesn't, then you did something wrong. So this number, negative 16t squared, cancels with this one. I'm happy with it. 32th plus 16h squared over h.
Factor out the H.
Factor out an h on the top.
Or, well, 32, yeah, 32t plus.
And cancel the h's. Oop, 32. 32t plus 16h. Remember, our whole objective is when the distance between T1, T2 become closer and closer, eventually zero. As h goes to zero, this number disappears. There is your rate of change. Let's see, what else we have? Actually, we forgot something. Remember, it's 32t, but we said in our equation, remember the first one, t equals 1? This is just a general statement. What do you think it's going to be when? So the answer you would give in the computer for the instantaneous rate, unless they give you any numbers, it would be this. That's the formula. But once they give you a t and the h goes to 0, then we get this number. This is the actual instantaneous rate, but this is the formula because we don't know what t is yet, and h is still there, but as it disappears, we get 32t. So it all depends on how the computer wants you to enter the data, the numbers. Do you want it with h or without h? Or as h goes to infinity or 0, or is it gone to 0? So let me see. Yes, yeah. No, I'm trying to see if I can find some of the numbers. Any questions so far? What time we get at? 12:20? Okay. Graphically, what do average rates of change, what do slopes represent? Graphically. Yes, but line where? How? Through a graph. Well, okay, yeah, what you're defining there is a linear equation is how it's one, for a linear equation, it's a relationship from one point to another point, rise over run. The average rate of change in the general form can be graphed as a secant line. Because yes, if you had a slope, average rate of change of 2/3, and I gave you a point at 1, 1, since it's a linear equation, all the points will have the same relationship. So I go up 2 over 3. Up 2 over 3. Up 2 over 3. Yes, so it is a relationship from one point to the next. But the beautiful thing about calculus is now we're not limited to just linear equations. And that was the whole purpose. That was the whole struggle by Leibniz and Newton, was figuring out, okay, what's the rate of change of a curve? Everything we know so far is with lines. So with what they had when they first begin, you have x1, x2, that corresponds to f of x1, f of x2. That's the secant line. That doesn't tell me the slope of the curve. And that's why we define this distance as being h. So that's what we're saying is, now as we make this one get closer to x1, we're saying that h, the distance, becomes 0. So as they get closer to each other, these are all secant lines. Eventually, when they get over each other, what do we have? This is a secant line. Eventually, what we're looking for is that. The tangent line. That is our whole objective. We want to look for the slope of the secant line through 2 points in the curve. Our goal is getting the slope of the line tangent to the curve. That is our objective. We're going from here to there.
Because this point goes down the curve.
Right.
The distance. Then that becomes a tangent line.
Right. So let's look at this.
The tangent line is when it's on top of it, or just-
Right. Well, let me. I have some items here. I'll use these. Okay, so here I have 2 points. I'm going to draw a line. That's a secant line. It doesn't tell me the slope of the curve. So I pick another point. Remember, h is getting smaller now. This is h1. h2 is a lot smaller. So h2 is less than h1. We'll cut that in half. h3 is even smaller. Eventually, when there are no more h's, what we have now is the slope of the line tangent to that curve at one and only 1 point. That's the rate of change. And the applications are endless. Businesses want to know, okay, if our profit and loss stuff looks like this, find out what's happening at this point. How many items are we selling it at per day to make us go down? What is our optimal values? In downhill skiing, same thing. I'm going downhill. This is the time. This is the speed. At what points do my speeds change? Then you could overlay this on the track and see exactly what's happening. What is the shape of the curve of the slope of the mountain when you're slowing down? Should you be slowing down, or should you be gunning it? Or I know a lot of people, if they go on a double black diamond, when it goes like this, they're going to do nothing but snowplow the entire way down. So no, once you go down, you just make smaller turns and you have a lot more fun. You finish the ride much faster. So, and that's what they look at in skiers, all sorts of stuff. Tennis players, the game itself. You're missing during the whole match, you make more mistakes during this time period. Why? What's going on? How do you feel? Are you exhausted? Is it too hot for you or what? At that point in time, exactly. And that's why it's instantaneous. What is exactly happening at that point? Let's see when my next example is going to be given. So let's define an average rate of change. The average rate of change of y equals f of x with respect to x over the interval x1, x2. Actually, it's an interval, so I use brackets. If I use parentheses, it's a point. The average rate of change of the function y equals f(x) with respect to x over the interval x(x) is defined as delta y over delta x is equal to f of x2 minus f of x1 over x2 minus x1, which is equal to f of x1 plus h minus f of x1 all over h, where h cannot equal 0. What is, remember, it's a curve. Slope of a circle at a point. How would you define that? Okay, we have the center. Let's say we have a point here, right? So we have to have the tangent line. We'll call that L. That's our center, and this is our point P. So how would you define the slope of a point on a circle? The line L is tangent to the circle at what point? At point P, and what else? We have to relate the center because it is a circle. And what do you call this line? What's that? What's that?
That line, the paper line is radius. It's from the center, right?
Right. Okay, yeah. And that's what we look at. That's basically, we're skipping a lot of extra stuff, but this is just the brass tacks, yeah, which is the radius. So the slope of the line is the slope of the line tangent to the circle at a point P. And it has to be perpendicular to the radius. Why is perpendicular to the radius important? And then my question is, aren't all tangent point lines perpendicular to the radius?
It's important that it's perpendicular to the radius, because if it wasn't, then that means it would be intersecting with another point.
Exactly. If it wasn't perpendicular, that means it wouldn't be a tangent line. It would be a secant line. Exactly. So I said, by definition, tangent lines has to be perpendicular to the radius. Because, yeah, if it wasn't, then it wouldn't be.
The secant line intersects 2 points.
Mhm. Or on a curve, any curve. Because if we had, say we had a cubic function, and I want to know the rate of change between these 2 points. It's a secant line, because I'm looking at these two, but even it's just collateral damage. So it's always as h gets smaller, so as this one gets closer to there. So you notice the values will drop and then get bigger. Right, but then we get a tangent line at that point, because it's just touching the curve at that point. But unfortunately, it's going to cross it has to, because it's just nature of the curve.
But that specific point.
Yes. It's just glancing at the point. Yeah, just forget about the rest of them.
Yeah.
Okay, let's look at example 3. Because all this stuff you'll see is important when we start defining what exactly is a limit, what exactly is a derivative, what exactly are we looking for in all these things. Okay, find the slope of the tangent line to the parabola y equals x squared at the point 2, 4 by analyzing the slopes of the secant line through 2, 4. Okay. Write an equation for the tangent line of to the parabola at that point. So what do we do first? What formula are we going to use? Right, but we're looking for the slope of the line tangent to the curve. Looking at the slope of the secant line, so it's delta y over delta x equals f of x 1 plus h minus f of x1 over h. That's what we'll have to look at. And you're right, since y is equal to x squared, it's going to be x plus h squared minus x squared over h, right? What else do we have to put in there? Because remember, the whole purpose of this is to only use 1 point. And so the only point we have, the only x value we have is 2. That's where it has to cross that. So this becomes now because that's our X value of our point. Again, we have to FOIL this out. What always has to be true? Anything after the minus has to cancel? That's our delta X, delta Y over delta X. But as H goes to 0, then becomes 4. So as H approaches 0, our solution approaches 4. But we're not done yet. Write an equations in tangent line at this point.
So what we just did was C.
Right, we found the slope of the tangent line. We found the slope of the tangent line of the secant line, yeah, because it starts off that one, and we're getting close. So we found the slope. That's the slope of the tangent line. How do we find the equation of a line? This was A.
4 equals.
So to do B, we're looking for y equals mx plus b. We know m is 4 and the point is 2, 4. That's x and that's y. Only thing we don't know is the y-intercept. So the y is 4, m is 4, x is 2, so plug in m for that one and b for that one, and we have our answer. That's the equation of the tangent line, of the line tangent to the curve at that point.
We got there, we found the slope. And then we just found.
Right. That's all there's to it. Exactly. Algebra. Calculus is the first part, then the rest is algebra. Look, another example. The figure below shows how the population P of fruit flies, Drosophila, grow in a 50-day experiment. The number of flies was counted at regular intervals. The counted values plotted with respect to the number of elapsed days, and the points joined form a smooth curve. It's supposed to be colored blue. Find the average growth rate from day 23 to day 45. Yeah, but it's printed it didn't. The way you do it, remember, these are the days. What axis are days represented? Time? X values. We need to find the points. We need to find X and the Y corresponding to it. So if X was 23 and the X was 45, what are the Y values? So at 23 equals 150. And at 45, 45 is here, 340. We have our 2 points. The average growth rate is the same as the average speed. So what's the formula? There's equal 8.6. Eight point six. 8.6, what are my units? The time is in days. And flies per day, yeah. So 8.6 flies per day. But this average, is it accurate for the curve? No, because it's the secant. I want the tangent. From the graph below, how fast the number of flies in the population growing on day 23? What kind of change is this? Instantaneous. So how do we find the instantaneous? Here we have to remember how we did using Excel, because when we did it instantaneous, you have to get H as small as possible, which means we have to get our vertical values from or here and here and here. Try to get closer and closer and closer to 23. Oh, 20, yeah, or 20, actually 25, I go 30, 27, 25, 24. And just try to guesstimate what that is, because we know that 23 is 150, 25 is 200, so 24 is approximately at 275. So do those calculations there. So we have at 23, 150. We have 24 at 175, 25 at 200. Let's try one more. 2.1, 2. Let's try 4. 27. Let's try 30. Make it easier for us. 30 is about 260. Yeah, so all you're really doing here is doing f of x2 minus f of x1 over x2 minus x1. You're just doing simple slopes. Okay, that's between these two. Now between these two, then between these two.
Those are gonna keep giving us secret lines. They get closer.
Right. Well, this should be the furthest away, then we get closer and closer. The closest one should be 25. So what's this one gonna give us?
Or I'm sorry, 50.
It can't. Because it's an increasing slope. 25 is here. 24 is here. Ideally, what you do is pick some numbers that are easy to calculate, but that's why I hate these. I'm sorry, you can see my graph. What did this one give us? 20, we had 200 minus 150 over 25 minus 23. Also gonna give us 25.
Okay, so
Stupid flies.
we just asked.
So are you sure? Is that gonna give us the same thing? 175 minus 150, 24 minus 23. So the rate of change is the same then. So with that, then we can say that at 23, at day 23, our rate of change will be 25 flies per day. Because we're approximating it.
Or instantaneous.
Our instant, yes, yes. Or instant, yeah, good catch. It's, yeah, because we're only as good as our data. And our data is how good we can read these charts. So that's section 1. To summarize it, average rate of change versus instantaneous rate of change. What's the difference?
It's gonna be taking it over the entire, like all the data.
But it's over what kind of graph? What kind of line? Yes. Average rate of change is the slope of the line secant, the secant line. Through the curve at 2 points h units apart. Right. is H goes to 0, right? I hope you wrote that, because now you see how my scribbling out.
Oh, no, I'm just using it for notes.
I'm gonna send you all these.
Okay.
Yeah, so I'm just getting myself, now that the whole semester started and everything, as soon as I get home, I scan these, download the videos and send you the files. So I'll be much faster on that. So before you go to bed tonight, actually, I'll see, all depends, because today we have meetings. So as soon as I get home, I'll send you a message when I do it. Actually, I'll do it both ways. I'll put it online. And also I'll attach it to a remind message, so you can have it right there.
That's good.
Right space?
Yeah. Yeah.
I only using system messages, like you say, so the link that you.
Okay, let me show you. You go in like normal, you get to Dallas College space, go to eConnect. Same way we did Blackboard. Log on. Our semester, so our calculus course is here. For you guys, all your assignments will be here. Lecture videos and notes.
That's really good, because then you have to miss the class directions.
Yeah, so even if you miss class, you'll have it right here. So, and unfortunately, you see, we only have notes for day 1 and day 6. The other days, we did stuff in class, the practice test and stuff, which I'll send you the worked out solutions there. And a day or so, I missed it. So now we should be getting back. I hear the cheat sheets also. But also, if you go back to here, if you look on the right left-hand side, you see what you guys. Here's what you guys will see. And also, I attached PowerPoint slides because there's people asking for PowerPoint slides. They want to supplement what's going on here. So more power to you. But you don't need to, because I summarize it all for you. Yeah, this is where I'm gonna post everything. There's your textbook. There's the class. Yeah, so when you go inside here, you look at that. You can also start surfing around over here on the left-hand side. You have your PowerPoint slides, you have your notes, you have your everything you need right here. So if you want to go to your homework. Yes, actually, now you should be able to start your homework on. So we've done these 2 guys already. And I'll give you all hundreds on those. Here's the media. Again, it's videos, the publisher created videos and some other stuff. And here's homework. But remember, on my stuff, I will send you the lecture notes, and the solution slides are already up there. So you can do this. I'm not going to tell you what to do. It's whatever works best for you. That's my entire goal in this course. So
When should we take the first chapter 2 test? You're saying that.
if you look at all these due dates, they're all saying the same thing. December 7th.
Right, I was just wondering,
To be on, see, because we took so long doing the review tests, which trust me, I don't mind at all, because I would rather spend all the time we need to be in the semester and then pick up the pace later on. Typically, we're going to cover a section a day, 2 sections a day on the average going out from here on out. Because as you see, I mean, we don't have that much really. We have 6 sections in chapter 2. We have 8, yeah, so we'll be cutting it close, But in chapter 6, we don't have anything. So we just have to do chapter 5, 4, 3, 4, and 5, really. And couple of these sections are gonna be super easy, I'll give you all shortcuts to do this stuff, and you'll be finished the homework in no time. So there'll be other ones that'll take you forever, but on the average, we'll finish the course in time.
I don't mind spending as much time. I just want to get a solid base.
And so is it just keep that, just every time we finish a section, go home and do that homework. And that'll keep you on pace to being finished.